Measure of position and box plot. So first let's look at measure of position. One ideal measure of position we're going to look at is called the z-score. If x is a data item in a sample or population with a mean of x bar and a standard deviation with s, then z-score of x is calculated as follows. It is x minus the mean value divided by sample standard deviation. So this z-score is for sample. This z-score is for population. Okay. So what does z-score measure? It measures how many standard deviations the x value is away from the mean. So the z-score tells us how far away a specific numerical value or the data is away from the mean using standard deviation as a unit measure. So this one is unitless because we're dividing by standard deviation. There's no inches, centimeters, kilogram. This is a unitless number. We're already counting with standard deviation. So let me do an example here to demonstrate what I mean by this. So let's read this example. Two friends, student A and B, who take different classes, they're different classes, have midterm exams. Student A score was 86 and B score was 78. Based on the z-score, which student did better given the class data shown below? So let's find the z-score for student A and student B first. So for A, the z-score is, we want to know the score of 86. How far the 86 is away from the mean. The mean for student A's class was 73. So minus 73 divided by class standard deviation of 8, which gives me 13 over 8, which is 1.625. Okay, so what does this number mean? It's very important to interpret the values, not just get the numbers. So let me write down what does this mean. This means student A scored 1.625 standard deviations above their class mean. So student A score is 1.625 standard deviation above its mean score of 73. That's what it means. How do we know it's above? Because z-score is positive. It is possible to get negative z-score. That means the mean value is, or the value is less than the mean if you get the negative z-score. So let's find the z-score for B. B score was 78. So 78 minus the class mean score for B's class was 69. So subtract 69 divided by standard deviation of 5. So then I get actually 1.8. So what does this mean? Let me write it again. Student B scored 1.8 standard deviation above the class mean score. So what are these scores telling us? So the question was, which one did better based on the z-score? Of course, if you just look at the scores, 86 is greater than 78. So we could just simply conclude that student A did better. But the question is, based on the z-score, which student did better given the class data, right? So we need to compare they're in different classes. Because student B score was 78, has z-score 1.8, it had higher z-score compared to student A score 86 has z-score 1.625. So this means the student B score higher relative to their class compared to student A. So let me write that summary. Student B did better compared to his or her class because student B's z-score was higher than student A. That means relatively student B did better among in this class, the class student B is in, compared to student A, whose z-score was little less than student B. So that's what z-score tells us. It helps us compare even data sets that come from two different classes or two different groups. Percentiles. Percentile means if approximately n% of the items in a distribution are less than number x, then x is nth percentile of the distribution, which is denoted by p of n. And we write usually a number here. So let me explain this with a number. If you score 73 percentile on SAT, this means you scored higher than 73% of all the people took the SAT at the time. So among all the people, you score higher than 73% of all people took it. So if you're at 99 percentile, that means you score higher than 99% of all people who took the SAT at the same time. So it's comparing the data within other data in that set. Okay. Does this necessarily mean that you got 73% of answers correct? No. Because percentile is within the distribution, is showing your position. Right? We're doing measure of position right now in this video. So no, this does not mean you score 70%, you answer 73% of the questions correct. That means whatever your score is, you're at 73 percentile. You score higher than 73% of all the people. Quartiles. Quartiles divides data into 4 parts. When we're finding quartiles for any set of data, they're in order, least to greatest. Second quartile is just the median. And the reason I wrote second, first, third in this order, not first, second, third, is because this is the way we usually want to find these values. So first we find the median, the way we learned before. Q2, also known as Q2, is just the median. And then first quartile is the median of the below Q2. So median of first half of the data. And third quartile is median of the above Q2. So it is median of the second half. So let me demonstrate with the example how we find first, second, and third quartile. So find the 3 quartiles for the data below. So Q1, Q2, which is median, Q3. So we usually want to find Q2 first, median. So this data is already in order. In order from decreasing to increasing. So then we can tell that if you count it 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 numbers in each row. And we have 4 of them. So for median, we look at 2 middle numbers. We have 40 numbers. Total size of this data is 40. That means for median, what we have to do is look at the middle 2 numbers, 65 and 66. Those are the 2 middle numbers. So for median, we add those 2, which is 65. Circular right here. 65 plus 66 divided by 2 gives me 65.5. So 65.5 will be right here, or we can think it's right here. So essentially, 65.5 divides the entire data into first half or second half, below Q2, above Q2. So this right here is below Q2. This right here is above Q2. So then for Q1, we're just finding median in the below Q2, first half of the data. So we're 20 numbers, so then we look at 2 middle numbers, this one and this one. Add those two and divide by 2, since we have even number of numbers. So essentially we're just finding median again for the first half of data. So 59.5 is the Q1. And let's look at Q3. Is 69 plus 70 divided by 2. Those are the two middle numbers. 69 plus 70 divided by 2, which gives me 69.5. So these are Q1, Q2, Q3. So using the idea of Q1, Q2, Q3, let's look at 5-number summary and box plot. So let's look at 5-number summary first. 5-number summary refers to minimum, Q1, Q2, which is median, Q3, maximum. We call these 5 numbers 5-number summary. And each of these numbers, because quartiles divide data into 4 parts, between each of these numbers, we have 25% of data. So there's minimum, Q1, Q2, Q3, maximum. And when I say 25% of data, we're talking about number of data. Okay. So if I have 100 data, 25 data will be here, 25 data will be here, 25 here, 25 here. Okay, so that's 5-number summary. And interquartile range measure is a measure of spread of middle 50% of the data. So interquartile range is just distance between Q1 and Q3. So we can calculate this by Q3 minus Q1. And box plot summarizes this 5-number summary. So let me actually put it this way. So in a box plot, this dot right here, this number refers to the minimum value. And this dot, this number, this numerical value refers to maximum. And this number right here is Q1. This number is Q3. And this middle vertical line is Q2, the median. So that's what box plot is. So let me do an example of given a data set, find the 5-number summary, find IQR, interquartile range, and draw a box plot. The first, data must be in order. So put data must be in order. Put in order. But this is a let in order. Just for convenience, I'll put in order. So it's a let in order. So if it's not, make sure to put in order first. So once we put in order, already in order, then we find Q1, Q2, Q3, and minimum, maximum. So we know this is the minimum. Maybe just different color, that may be confusing. This is minimum. This is maximum. So we find 2 out of 5 numbers. Median, we find it by, look at the middle number. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 60 numbers. That means we have even number of numbers. So where's the middle? They're 8, 1, 2, 3, 4, 5, 6, 7, 8, right here. So then we should have A numbers here. We'll do it better. We should have A numbers here and A numbers here. So median, we add those two middle numbers and divide by 2. So Q2 equals 14.9 plus 14.9 divided by 2 gives us 14.9. So let me highlight all those numbers we found so far. And then for Q1 and Q3, Q1 we look at first a number, first half, and middle is right here. So we add these two and divide by 2. Divide by 2 gives us 6.6. So Q2 is 6.6. And lastly, Q3 right here. Add these two numbers, divide by 2, and you get 23.4. So that is Q3. And interquartile range is Q3 minus Q1, which is 23.4 minus 6.6, which is 16.8. Okay, so now that we found five number summary, let's draw a box plot. So when we draw a box plot, the first thing is we must draw a number line. Okay, like this. And then what I'm going to do is I'm going to mark. Let's start at 0. And let me increase 5 at a time. Okay, so make sure to draw a normal line first. And then we mark this number. Minimum is 0.8. Somewhere here, minimum. Minimum. Right here, 0.8. Maximum is 42, so around here. A little bigger than 40. So we draw a dot on minimum maximum. And for Q1, Q2, Q3, we draw vertical lines. So Q1 was 6.6, a little bigger than 5, so somewhere here. We draw a dot and draw a vertical line. Q2, the median is 14.9, close to 15, so somewhere here. And Q3 is 23.4, between here, so around somewhere here. And the middle, Q1, Q2, Q3, we connect these to make a box. And we connect these dots. So this is the box plot, a box plot representing this data. So box plot has many benefits. One benefit is we can pinpoint the median right away. And also we can see if it has an outlier or not. We can tell that this number seems large compared to mid 50% of data, right? So, I mean, with this, we can't 100% conclude if this is an outlier or not, but it kind of gives us a trend. It has such a kind of an extreme value. So the box plot is also can be related to the shape of distribution, especially relating to the histogram. So box plot can also be put into 3 categories: skew right, symmetric, and skew left. So if you have a box plot looking something like this, right here, this box plot has shape of skew right. We can think as like this. Just like this histogram, skew right. And it can be also symmetric and skew left, similar to the distribution. And the reason this could be important for box plot is box plot itself doesn't tell us the mean value. But knowing the distribution, we can compare the location of a mean and median. Because when it's skew right, we know that the mean is right side of median. So mean is bigger than median. For skew left, mean is smaller than median. So mean is left side of median. For symmetric, the mean and median are very close or they're equal to each other. So let's look at examples. Identify the shape of distribution and determine the 5-number summary looking at this box plot. So this box plot, very similar to the one skewed right. So we can see that this one is skewed right. Skewed right. And looking at the box plot, we can find out the 5-number summary. We can tell that 0, minimum is 0, maximum is, let's say, about 16. We're estimating here. And the median, Q2, is, let's say, about 3. In Q1, Q3, we can find by looking at this number. Around 1. This is maybe around 6. Okay. So we can also read off those 5 numbers from the box plot. Although here we have to estimate a little bit because the grade is increased by 5. But it's close enough. So let's look at this problem. Analyze the box plot. We have 2 box plots in this example. So first, let's determine its shape. This one is symmetric. The X is symmetric, where the Y is more of skewed right. Skewed right. And let's also find the median. Median for this one is about 31. Wherefore for X, the median is about 40. Median is about 40. So those are just observations we can make just looking at each individual box plot. Now let's try to compare these two. We can make some observation, right? First of all, the range on Y is bigger. The difference between difference between the minimum and maximum is greater in Y. Not only that, the interquartile range for Y is also bigger. Right? So what can we conclude about this? Y has more variability. Because range is bigger, we can say that the whole data set range is in bigger number. Also, interquartile range is bigger. Another thing we can conclude is X would have a smaller standard deviation value compared to Y. That's because, first of all, X is symmetric. That means mean and median are very close if they're not exactly equal. And because it's not as spread around compared to Y. So the X compared to Y, data is close to the mean compared to the Y. Because remember, standard deviation measures the spread of data. So in general, when we are comparing box plots, the data with a larger standard deviation is the one with greater spread. So in this case, Y has a greater spread looking at the box plot. So Y would probably have a bigger standard deviation compared to X, which means X would have a smaller standard deviation compared to Y.